Okay, so welcome everyone to this session on structural optimization. The intent of this session is on what you need to do to successfully perform structural optimization specifically. So what we'll talk about is physically what optimization actually means. We'll have an example model that we'll use throughout this session. First, then an example of how things goes wrong, and then the better and more correct approach. Some confusing issues that sometimes crop up when we perform structural optimization, some additional notes on things to look out for, a brief summary of different types of optimization, and then what else we can actually use it for. So the first one is, what is optimization? So intuitively, we want the best design. The problem with that is it's not a very mathematical or structural way to describe this. So mathematically, we need to, in some way, specify what does best mean. So if you perform what's called classical optimization, this is typically what you'll do if you attend some kind of a training or classes on optimization. And I have to at this point say that what we'll explain in this is exactly what structural optimization actually is. But there's very specific requirements and usage methods and so on for structural optimization, which doesn't so much differ, but if you're not careful how you implement it, you'll run into issues. So in classical optimization, we have something called the design variables. These are the things that can be changed. Something like plate thicknesses would be in one analysis type. In certain analysis type, it could be which material can be removed or kept. The second one is the cost function. So that is the target that I want to minimize, because that's effectively what this is. It's a minimization algorithm that needs to be run to find the minimum of something. Now, in some cases, we also use the option to maximize it, but the difference between the two is if my algorithm can only maximize, I just multiply the cost function by -1, and suddenly it becomes a minimization problem. Then we've got constraints, and there's two types. So this is where we specify limits to the input, in other words, the design variables. A good example would again be plate thicknesses. It's not allowed to be less than X and greater than Y. But also, and this is very important for structural analysis, is limits to response. In other words, a result. Okay, so here's our example model. This is just a simple example of a model, but it can be more complex. So what we already have effectively, and the first couple of these are pretty much what we need for a normal structural finite element analysis. So there's nothing special for that first bit. So we've got a baseline structure, something that physically we can model, mesh, simplify as needed. We need one load case. For optimization, I need to specify what can change. For this example, it may be the thicknesses of the webs and the flanges and stuff. Also limits on those. But then the one thing that we have at this point is this general idea. I want to optimize the design, but I have no idea what optimum really means. It's probably something like I want it lighter or something. Now, exactly the same holds if I have a more complex structure, whether it's a full-on vehicle model, part of a vehicle, some kind of a drone or something. For all of those, we have the same kind of concept. We want to improve something effectively. We want to get the best design. Now, starting with this, and on purpose not defining this really well, this is how things pretty easily goes wrong. So the classic method is we try and keep it simple, do a simple test model, and for this case, we made it too simple. So we say, I want to minimize mass, but I don't apply any constraints. So what's going to happen? Well, the optimization fails because since I don't specify limits on what I can do, all the material will be removed. So effectively a zero mass part. Okay, so then we say, I need some kind of a limit. So we still keep the same. I still want to minimize the mass, but now I want to limit the design variable. So in other words, something like dimensions. Think again of that I-beam section. So in that case, what will the result of this be? Well, pretty much the same as before, except each of my dimensions will reach some kind of a minimum level. If I say between 5 and 10 mil plate, it'll reach 5, because it simply says based on this information, the minimum mass will be when everything is at its thinnest. But then I run the analysis and I see that my stresses explode. So then we step back a bit and say, okay, let's change direction, but now minimize the stress and limit the design variable. So then the opposite happens, because all dimensions now reach the maximum allowed levels instead of the minimum. So the mass is the highest that it can be. Stresses are probably pretty low, but it pretty much didn't do anything. There's no optimum in this approach. So now we try a totally different way. And this is something that you see a lot in classical optimization, where we specify some kind of a cost function that's a combination of a couple of things. In this case, I can do something like minimize some coefficient times stress plus a different one times mass. Now you have to be careful with units. If it's in millimeters, this will be a low number. If it's in in meter units, stresses will be really high. So you have to scale it reasonably. And again, none of this is a great way of doing things. But this is if you try and follow how this typically behaves. So we still limit the design variables. So at the end of this, we get some kind of intermediate result. It's not at the minimum, it's not at the maximum, because I'm weighing it to both. So based on these coefficients, my stress may be too high or too low, and the mass is somewhere in between. Now the problem is if the stress is too high, I can tweak that coefficient, make it higher, or make this one low. So I weigh it more towards stress. So I tweak the cost function coefficients, and now I get something similar, just different results. So it's still an intermediate mass, different stress state, different mass. And at some point, let actually an optimum design. And the answer is probably not. Now, things go even worse if we start looking at more detail. So if the coefficient change, you get a different optimum. So which one is actually the optimum? So effectively, it's one of those, I can change the answer, and I define optimum by simply changing coefficients, which is a terrible way to do things. So we have no idea of knowing whether the coefficients are correct or even reasonable. But it gets worse. What if I have a second load case? Very few structures have a single load case. So if I do that and I try the same approach, now I need to include this into the cost function in some way. How do I include it? And then also, what should my new cost function be? Because the coefficients be, because the previous coefficients wouldn't work for the new one. So that's a really bad way to do things. So the better and more correct approach for this kind of an optimization is we start, and I've shown you all the settings that didn't change from the previous one. The only thing that I add there is a better understanding of what an optimized design is. So arguments like in all of these cases, I want minimum mass. So my new statement may become, I want the lightest design that can do the job. Do the job may mean it doesn't fail, it doesn't deflect too much or something. So from this, I can derive all my cost function and design variables and all of that information. Okay, so the design variables, hopefully we know from before, that is the stuff that can change. So the question for the cost function is simple. What do we want to minimize? If I look at that statement, is I want a light design. So the lighter the better, meaning I want to minimize the mass. So that means I don't include stress or anything in the cost function. I simply want the lighter structure. The second one is constraints. So that says this can do the job. Another way of saying it is it's a valid design. A valid design is one that doesn't fail any of its limitations. So in other words, I'm not outside of my thickness ranges for plates that I've allowed. The stresses doesn't exceed some values and so on. So we've got design variable constraints, which is, as I said, something like plate minimum and maximum thicknesses. But we also have response constraints, which is the one thing we didn't actually look at in the first one. We looked at responses, meaning stresses and displacements we calculate in the analysis. And for those responses, we try to force it into the cost function. effectively it's actually a constraint. So what we do for that is we say the stress should be less than some limit. Displacement should be less than some other limits. If it's a buckling analysis, I can specify that the buckling factor has to exceed a certain level. For natural frequencies, arguments like the frequency should be above a certain level or not in a certain range. And we can define this per load case. So let's say I've got 10 load cases. For load case 1, stress should be less than 200 MPa. For load case 2, it should be less than 250. Whatever the case is, they can be the same stress. You can have different ones. So what we get out of this is a structure that's got a low mass, but not the minimum possible if I look at my design variable allowances. But some of my design variables may and most likely will be at the limit set. So again, if I said my stress should not exceed 200 MPa, I'll get 200 MPa for at least one load case in most cases. The only case where that doesn't happen is if I'm not allowed enough design variables, the thickness of parts and so on. So you may get to the point where I've said anything from 10 to 20 millimeters, and if I run it at 10, the stresses are actually still too low. So then in theory, I can use a thinner part. Okay, so it's a very likely, sorry, the first one is design variables will be most likely at limits, but some of the results will also be at the limits for at least one load case. So that's a very common one. Now, this means design is valid, meaning passes the requirements. I'm not outside of the allowed thickness and so on ratios, in other words, design variable ratios. And my results are all within key requirements. If you arguments like you have to do a code calculation, one of the requirements may be that the stress for this load case may not exceed X. So in that case, these are the stresses and these result limits that we specify. So valid, in other words, means none of my limits are exceeded. I'm entirely within the allowed range. So in this case, I've got a minimum mass, meaning it's an optimal design, because minimal mass in this term specifically means if I change any design variable, either the mass will increase or I'll exceed the design limits. So in other words, I change the variable by a small amount and the stress comes down or stay the same, but the mass increases. Or even if the stress decreases, the stress now exceeds the limits that we've placed. Okay, so then we have a question I've had a couple of times. So if we stand back a bit, and now we've run 10 load cases. Each has its own stress limits, displacement limits, whatever. So which of these load cases did we actually optimize for? And the answer is it's totally the wrong question, because we didn't optimize for stress, we optimized for mass. Stress is a constraint. Variables, meaning if I specify every one of my design variables a number, I've got a fixed design. I've specified my plate thickness for plate 1 is 10 moles, for the next one is 12, and that is my design. So there's one mass associated to this. We don't have a separate mass for every load case. The stress is different for every load case, but every load case has its own stress limits. There may be additional limits. But a valid design, in other words, is when none of these limits for any of the load case is exceeded. So effectively, we're not optimizing for a load case, we're optimizing for this part not to fail, and then find the minimum mass of the part which will not fail. And that's for any of the load cases. So another way of saying it, find a valid minimum mass design. So some complications with optimization, if you do a course on this, some of this you'll run into really quickly. So the first one is the concept of a local versus global minimum. So this is just a single design variable. In general, in FEM, we have anything from 10 to a million plus design variables. So topology optimization, every element has a, let's call it a there-ness ratio. 0 means it's not there, 1 means it's fully there. So plotting this in n dimensions is going to be really difficult. But the same happens whether it's one dimension or multi-dimensions. As I change the design variable, it comes down, reaches some kind of a minimum, goes up, and then come down, and we have another one. So if this one, if I plot this from minus to infinity to plus infinity, and these are the only two minima, then this will be the global minimum and that local. Since we don't often do that, we don't often know whether we've actually reached a global minimum or anything. Now, if we think in terms of algorithms, so if I'm at that point for a guess, I find my gradient as well. If I increase the design variable, I expect it to come down. So I do that, and as I go past that, it now says if I increase it further, now the design variable increases. So it'll oscillate and hopefully settle on that point. If I start over there, it's possible that we'll end at that location. So that's one of the methods we can use to try and get to different optima and better optima, is to run it from different initial points. But there's no guarantee other than a fully exhaustive search, which is a really expensive analysis to try and find all the local minima. Okay, another one that you have to be aware of is if I say the stress is not allowed to exceed 200 MPa, then according to optimization, somewhere in my model, it will reach 200 MPa. And the reason for that is if it's less than 200, it means it can still take a little bit of mass because I set the limit at 200. Now that should worry you, and probably does. So you run an analysis and you're used to running an analysis where, let's say the stress limit is 200, I get 180, I'm happy, I sign off the design. But in this case, now my answer is 200 exactly. Now what? And that means my mesh have to be fine enough to capture a really accurate result. My stress limit is perfect, my material, everything. So we have to then, if we want to run an optimization for that as a limit, either reduce that limit a little bit to say 180 because I feel safer there, that gives me margin for inaccuracies in my mesh, or we have to mesh super fine to try and improve that result. Notice I said stress, but in general, we don't have a single stress. We have stress per element, effectively stress per node for the whole model. So there's actually lots of these. But what we can typically say is the maximum, argument's sake, for measure stress in the model is less than X. So effectively, I'm not looking at a single point, I'm looking at everywhere in the model. So just beware of this. Include this in your initial specifications. So if you don't feel comfortable with 200, if the code says 200, make that argument say 170, 180, 190, depending on, well, your model, your mesh, comfortable you feel with a slightly closer value. Another interesting one that we get, if I've got a large assembly and I separately optimize each part, and then I compare that to I optimize every part, but in the assembly itself, so simultaneously. I often don't get the same result. And this is due to, if I change one part, the mass, in other words, the load that's transferred to another part differs, the stiffness differs, and so on. So the stress state of the second part changes as I optimize the one. So because the parts influence each other, they have an impact on each other. So optimizing each part doesn't result in an optimized system, in other words, optimized assembly. It doesn't mean it's going to be a bad design. It's still probably going to be a good design as long as the loads for every one of these parts was at least reasonable to start off with. So instead of argument's sake there, my initial design, I may get that for my assembly if I optimize each part, while if I optimize all, I may get to something like this. Okay, another one is optimum. Not all optima are robust. So this is a surprisingly common one, where let's say this is what my cost function looked like as a function of design variable. So what this means is, if let's say that's my nominal design, I find that's about 2.75, and manufacturing tolerance says it can go from 2.5 to 3. So that's plus minus 0.25. If I look at that, I'm still in that range. So my cost function has actually increased by a small amount. If I look at that one, that's a better optimum. But if I change by that same amount, I go from there to there, I jump to those 2 points. So suddenly my manufacturing tolerances need to be a lot tighter if I want to stay in a range close to that. So be careful of just looking at an optimum on its own. It's always a good idea to have a look at what happens surrounding that optimum. In other words, is it robust? Does it allow me enough leeway that manufacturing tolerance will still give me a good answer? So it'll typically happen if I design for this Optima and I make 20 parts and I measure each of those. I'll see very similar behavior between all of them. If I do it for this, I'll see some great ones and some really bad ones. Okay, and then another thing that's super critically important in optimization is if you miss a load case, and at least an important load case, then the structure will probably fail in use because it wasn't optimized to look at failure for that specific load case. So that may include things like buckling, natural frequencies, modes to low, in other words, loads that exist purely when you assemble the structure. So a really stupid example would be something like if you design a rim for a racing bicycle. One of the loads that can actually break that rim is the load that you need to actually get the tire onto that rim. So that's some kind of a levering action. That's not part of the normal loads that it sees, but if it can't survive that load, there's no point in trying to manufacture it because it will fail. So this is something that you have to be really careful of. In general, structures that's not optimized tend to be less sensitive to stuff like buckling and so on because we've got a couple of plates that's probably a bit thicker than it really needs to be. But the closer you get to an optimum, the more important it is to ensure that you've included every possible method of failure. Otherwise, you get a sub-optimum design because it's minimum mass, but not a valid design. So when you manufacture it, the part will fail before it should, or it fails when it should not have failed at all. So let's briefly switch sideways a little bit and talk about different kinds of optimization. That's relatively common in structures. So the first one, I don't specifically have a name for this. We'll talk about property changes. I'm changing the thickness of a beam, dimension of beam or thickness of plates and so on. So this is just a number somewhere in a property. I'm not physically changing my model. I'm just changing some value. So the second one would be, and this is the other extreme, this is where we've got some kind of a complex 3D structure, a solid part. And I want to optimize, argument's sake, radii and stuff in there, or thin and thicken some sub-regions. So pretend this was a part that we wanted to machine. I could say, but there I want it thinner, there I want it thicker. So on that level, I either have to move nodes in the optimization algorithm, which is possible, or I can update my CAD, remesh, rerun, and you do effectively include the CAD in the recycling process. So both of these have got issues. If I move nodes, I have to specify in some way what is reasonable. So if I've got the radius that I want to use, so let's say with a radius along that length, and I want the same radius from there to there, I have to in some way specify what does it mean in terms of the movement for every one of the nodes along there relative to my design variable, which is the radius, which is surprisingly painful to do, but entirely possible. It's definitely not impossible. Well, for the updating CAD, if I make the radius smaller, I also need to mesh finer in that radius, otherwise my error becomes larger. So you have to be really careful if you do this to ensure that you've got a fine enough mesh or measuring the important locations away from stress concentrations. The further advantage in terms of performance is this one is relatively fast. The model doesn't physically change. It doesn't need to remesh. This is a new CAD model, a new remeshing operation, and run the analysis. And even if that is included in a single analysis, it's something that needs to fire up effectively CAD and a remesh operation. I'm not leaning towards either of these. I'm just trying to explain what the differences is between the two. Okay, then we get to something like topography. So simple vehicle model, the one I showed at the beginning, is actually a good example. So this is where we don't actually change the mass. We're trying to either reduce the stress or increase the stiffness or possibly a combination of the two. And the way we do that is by shaping. See, the roof is not flat. It's some kind of a bend shape. If you look at the bonnet of a vehicle, it's the same. Almost every single part, probably every single part there isn't a thin, flat section. They're shaped in a specific way. Now, that shape dramatically improves the natural frequencies, the stiffness of the part, the strength of the part, and so on. So that's the purpose of topography, is to just move nodes normal to the surface. Again, topography is not just a random movement, because if I move one node up, one node down, one up, one down, that's not really physical. I won't be able to manufacture something like this. So we have to kind of, in some way, specify the size of features or minimum sizes of features to be able to do that. Then we have something like topology. Topology simply says we remove elements from a structure. So on purpose, it's a very simple one, but there you can see these. It's really jagged there because it was a perfect X mesh, but it's removed the elements in those regions. So the output of this is not directly useful. It's indirectly. If I smooth that, yes, that becomes useful. Or alternatively, let's say I want to create a part that's welded out of subparts. This tells me where the material needs to be. So this is not a great example, but often for those kind of structural, you'll see, but I need some kind of a ribs or welded parts in specific regions and so on. So based on that, we can then manually generate a new CAD model of where the right stiffness and the right material is. And then we can go back to one of these methods again to try and optimize what those plate thicknesses should be or what the radii should be and so on. So update the CAD effectively. Then we have what's called generative design, and generative and topology has the same intent. The approach differs slightly. Well, so relatively significantly. But the intent is the same. It says we've got some kind of a volume. In this example of the plate, I start with where material is allowed, and then I say remove material. In this case, I also start with where material is allowed, interfaces where it needs to be bolted or welded or whatever to something else. And then we say remove material as you go. And one of the main difference between these two is this one, we start with a fixed mesh. And I can't remesh this as it progresses. This one, the way that it works, it automatically smooths it every step, so we actually get better stresses. There we'll have these really high stress in the corners, making topology kind of difficult for stress optimization. While in this case, since it's smoothed, we get better stress responses. It also allows, as it progresses, since there's lots of material removed, it can now say, but in this region, let's use effectively smaller elements. So it goes through these multiple refinement processes. And the advantage here is at the end, I immediately get a 3D printable design. Or even if not, I may get something that's close enough, and then I may say, but I need to cut off that section cleanly. So I can take it into CAD and do minor modifications to get the interface and so on correctly. In all of these cases, we still have the requirement of where do I want to end and what is an optimum design. So with 3D printing, it's purely material. Often for structures, it's if you add too much machining locations, it actually adds cost, even if in theory, cost goes down. If I design something for aerospace, often we'll start with a pretty large piece of aluminium that we cut away a lot. So the cost there isn't related to the final material, because my initial material compared to the final, I may end up with less than 10% with the rest machined away. So that additional machining is actually more expensive. But the cost there comes in flying a heavy part is much more expensive than a lighter component. So that's why it's in that case really important to look at mass. Okay, now again, moving sideways in a slightly different way, other than something like structurally optimizing to ensure that the part is strong enough and it won't fail and the buckling loads are high enough, find the minimum mass, we can actually use optimization in finite element analysis for quite a few other things. A common one would be something like model matching. So model in this case is my finite element model, and I can match it to either I need a very specific stiffness distribution or something, or I've measured a component of the same thing. I want to match the two. I want to get my finite element model closer to my measured data. In some ways, it seems almost a bit like cheating. But as long as your changes are things like small changes in plate thicknesses and so on, because a 10 mil plate is not 10 millimeters. There's some kind of a tolerance. So as long as that's the case, it's entirely valid. A great example is anything that has to do with, if you send a part to SpaceX, one of the requirements is they have to have a model of it that's matched to the actual behavior. So you have to test it, update your model, and then send them a model that represents that as accurately as possible. So we can use this to match results or to measurements, in other words, or to some target. So certain way, certain stiffness distribution, or more likely I've measured some locations. So we can also use this to match modes. So how do I minimize the difference between my original model and what I want in the model? So in other words, a good example is modes. I ran the analysis and my first mode is at 10 Hertz according to the analysis. In the manufactured part, it was measured at 9.3 Hertz. How do I optimize? So I still have design variables I need to change, thickness and stuff, but how do I do that? So in that case, the simplest approach, and I'll explain the more complex or more complete one in a moment, is to simply say my cost function is some coefficient, and the coefficient for the moment isn't important, but it will become important in a moment. A coefficient times the difference between what the mode should be and what it is, and we square that number. If you don't square it, then the problem is my optimization will run in the wrong direction. We'll try and minimize a mode instead of minimize the difference between modes. Now that weight for that little equation comes in, what happens if I've got 10 modes that I need to match? So then I'll write 10 separate equations, mode 1 frequency minus the measured frequency squared, and do the same for everyone, but I specify different weight factors for each of them. If all of them are equally important, I'll make the coefficients 1. If a couple of the modes are really critically important, I can just increase the weight a little bit to try and improve that matching. By the same method, I can match displacement at a certain point or a number of points, or stress or strain distributions, strain gauge locations. So I can specify for this specific load case, I've measured a certain stress at a certain location, and now compare that to the finite element value there, subtract the 2, square it again, and try and minimize the difference between those two effectively. So the moment those two values are exactly the same, the difference is 0, meaning I've reached a value of 0 for my cost function. So we can also do it for similar things where we can say, I want to maximize the first natural frequency of my structure argument set. So within limits that you specify, and if you want, we can even specify mass now as a constraint to say, keep the mass the same, but maximize the first natural frequency. We can also, in certain, especially aerospace applications, but also everywhere where we've got some kind of a component that operates at a very specific frequency or speed. A very common one would be 3000 RPM, which is 50 Hertz for electrical motors. So that's normal, two-pole, as an example for this, a single phase motor. So for something like that, we don't want any components attached to it to have a natural frequency close to arguments like 50 Hertz, because we expect excitation to possibly excite, and if it does, strongly excite that specific frequency. Staying away from a frequency range would be very similar to matching mode. While maximizing a mode, a cost function becomes the negative of the frequency. In other words, we want to maximize, which is the same as minimize the minimum of the negative of, in that case, frequency. We can also do stuff like maximizing stiffness. One of the first implementations in MSc Nastran for topology optimization was for the purpose of stiffening the structures. You don't specify a stress limit. We specify the mass target and then say find the maximum stiffness for the component with that specific mass attached to it. Okay, so now that we're done with just some additional comments and so on, just step back a little bit and go back to the start. The whole presentation is about where do we start for structural design optimization. So the first and most important thing is we start with a well-defined requirement for the optimization. In other words, what does Optima mean for my design? If you can't answer that question, either find out or don't do optimization. So once you have that, that determines what your design variable should be, or well, effectively, you need to know what you can change, but these change what your cost function is, what your design constraints will be, and your response constraints. So design variable limits, stress limits and displacement limits, buckling limits, and so on, and mass in the example that we've used above. Okay, so then once you have this, so this at this point, it's still independent of the software you use. Once we have this, now we can go into the software, and that last bit is basic, at least understanding of how to use the software to implement the above. So for something like the sizing optimization, it's pretty easy to do. If you want to use generative design, it's a specific interface for a very specific purpose, so it's also relatively easy. Once we want to do things like minimizing the difference between measured results and simulation results, at that point you have to dig a little bit deeper to understand a bit more about cost functions and so on. At that point, it's not a simple minimize mass or maximize stiffness kind of an operation. Okay, so that effectively then is where we need to start with design optimization.